Welcome back to Revise and Resubmit, the podcast that takes, those really dense academic papers and makes them surprisingly interesting. I'm Pavlov.
And I'm Nikita.
We've noticed a lot of you are tuning in, which is amazing, but I haven't quite hit that subscribe button yet.
Yeah, and that little button, honestly, it's so small, but it makes such a huge difference in helping us reach more people with these important discussions.
Right. The drive to make things better, faster, smarter. It's fundamental, isn't it? Whether it's science or just, organizing your day better. And today we're digging into an area where that drive is taking some really fascinating steps forward.
Absolutely. We're looking at AlphaEvolve today. It's a new coding agent from Google DeepMind, and it seems to be really pushing the envelope in algorithm design.
AlphaEvolve. Yeah, the name definitely suggests something important. So break it down for us. What is it, basically? What's the big picture?
Well, think of it like this. It's an AI that can read computer code, understand it, and then actually rewrite it. But the goal is specifically make that code better. It uses these powerful large language models, the AI that's good with human language, but it applies that to computer languages. The aim is to take algorithms we already have and sort of evolve them, make them faster, or maybe find totally new ways to tackle problems.
Okay, so it's not just writing code from scratch. It's more like taking existing code and improving it through almost like natural selection.
That's a really good analogy, actually. It uses an evolutionary approach. So the AI suggests changes to a pool of algorithms. Then, and this is key, those changes get automatically tested to see if they actually work better, based on criteria you set. It's this cycle. Propose, test, learn. That's the evolution part.
And that automatic testing, that sounds crucial. AI can sometimes sound confident even when it's off track, right?
Exactly. You need that grounding. By having the AI's ideas tested by running the actual code, you make sure the improvements are real, they're measurable. And what's really interesting is that over time, this can lead to algorithms that are quite different from where they started. You might stumble onto completely new ways of doing things.
Okay, now that's compelling. So it's not just about tweaking things slightly. There's potential here for real, novel discoveries.
Precisely. The white paper suggests it can be used both ways, finding brand new algorithms, or just being a really powerful tool to find better solutions for problems you can describe with an algorithm.
Now, AI and algorithms, we've heard about this before. I remember something called Fun Search. How does AlphaEvolve stack up against that?
Good question. Yeah, Fun Search was definitely an important step. AlphaEvolve builds on those ideas, but seems to take it quite a bit further. For instance, Fun Search mostly dealt with pretty small Python code snippets, like just a few lines. AlphaEvolve, on the other hand, can handle much bigger complete programs. We're talking hundreds of lines sometimes. And it's not just Python, it can theoretically work with any language.
Wow, okay. That's a big difference right there.
It is. And Fun Search needed really fast evaluations, under 20 minutes on one machine. AlphaEvolve is more flexible. It can handle evaluations that might take hours, using lots of computers in parallel. Also, Fun Search often generated millions of potential solutions. AlphaEvolve seems to get great results with fewer attempts, maybe because it uses these newer, more sophisticated LLMs that understand more context. Oh, and a key thing, AlphaEvolve can optimize for several goals at once. Fun Search was focused on just one metric.
So it sounds like AlphaEvolve is, a much more powerful and versatile toolkit compared to what came before.
That seems fair to say. But there's one important similarity I should mention, like Fun Search. AlphaEvolve needs problems where you can automatically grade the solution. Machine gradable solutions. So naturally, it tends to focus on areas like math, computer science, optimizing systems, places where you have clear ways to measure success.
Right, that makes sense. You need a way to tell the AI if it's actually doing better. So how much human involvement is there? Does AlphaEvolve just run off on its own?
No, human input is definitely still vital, especially at the start. We, the humans, define the what. We set the goals, the evaluation criteria. We also usually provide a starting algorithm, though it can be pretty basic, and maybe some background info. Then AlphaEvolve takes over the how. It figures out the steps to improve things.
Got it. Set the target, give it a push, and let it run.
Yeah.
How do you actually tell it which bits of code to work on if you have a big existing program?
Yeah, they made that pretty straightforward. You use these special comment tags right in your code. #evolve block start and #evolve block end. Anything between those tags is fair game for AlphaEvolve to modify. The code outside those blocks just provides the context, lets the evolve part run and be tested.
Huh. That sounds pretty easy to slot into existing work. The paper also mentioned it works at different levels of abstraction. What's that about?
Yes, that's a really flexible part of it. So, depending on the problem, you might get AlphaEvolve to directly fiddle with the raw code. Or you could give it a sort of blueprint, like a function that builds the solution, and have AlphaEvolve evolve that blueprint instead. It can even evolve the whole search strategy it uses to find a solution. Or, get this, it can co-evolve intermediate parts of a solution and the search methods at the same time.
Co-evolving. That's pretty meta. So the way it finds solutions can itself get better.
Exactly. And the research suggests different approaches work better for different problems. Like, if your solution needs to be very symmetric, maybe evolving the construction method is best. For messier problems, maybe evolving a custom search algorithm is the way to go.
Okay, so we've got the process, the human role, the flexibility. Let's get into the generation part. How does it actually use these big language models to come up with the improvements?
Right. It uses state-of-the-art LLMs. The paper mentions Gemini 2.0, Flash and Pro specifically, and feeds them these really rich prompts. They can handle a lot of context. And you can customize these prompts heavily, give it problem details, equations, bits from research papers, whatever might help. They even use something called stochastic formatting, basically, slightly varying the prompt structure to nudge the LLM to think differently.
So it's not just randomly guessing changes, it's informed guessing based on all that context.
Precisely. And the prompts often include results from previous tries, the code, the output, the scores. That feedback helps the LLM figure out what works. Maybe one of the coolest bits is meta prompt evolution. The LLM itself can actually suggest ways to improve the prompts for next time. It's like it's helping tune its own instructions.
The AI is learning how to ask itself better questions, and these diff blocks mentioned in the paper, what are those?
Yes. When AlphaEvolve suggests a code change, it usually shows it as a diff. You see the old code marked maybe between search and ln, and then the proposed new code between element and replace. It's a standard way to show changes, makes it really clear what's being altered. Although for smaller changes or total rewrites, it might just output the whole new block of code too.
And why use both Gemini Flash and Pro? Is it like a speed versus power trade-off?
Exactly that. It's about balancing throughput and quality. Gemini Flash is faster, so it can explore more possibilities quickly, more shots on goal, Gemini Pro is generally more powerful, maybe a bit slower, but it might come up with more sophisticated breakthrough ideas. Using both lets AlphaEvolve cast a wide net, but also dig deep when needed. It's an ensemble approach.
Makes sense. Explore broadly, but also have the heavy hitter for the tough problems. Okay, so it proposes changes. How does it know if they're any good? The evaluation part.
So the core is this automated evaluation function. The user provides it. This function takes the proposed code, runs it, and spits out one or more scores, numbers that say how good it is. AlphaEvolve's job is always to try and maximize those scores. The function could be simple, does this equation balance? Or complex, run a whole simulation.
And that score is the bottom line.
Mostly, yes. But there are some optional, clever evaluation tricks too. There's something called an evaluation cascade. Basically, you run quick, cheap tests first. Only if a solution passes those does it move on to the slower, more expensive tests. Weeds out the bad ideas fast. Sometimes they even use another LLM call just to get feedback on things like code simplicity stuff that's hard to put a single number on. And of course, this all runs in parallel on potentially lots of machines to speed things up.
A multi-layered judging process. And it can optimize for multiple scores at once. Why do that?
That's right. You can tell it to improve, say, speed and memory usage simultaneously. That's obviously useful if you care about both. But even if you only really care about one thing, like speed, aiming for related goals too, like simplicity, can sometimes indirectly lead to even better speed. The idea is that considering different angles of goodness helps it explore more diverse, high-quality solutions, which might contain the key to improving your main target metric.
Interesting. Coming at it from different directions helps find the best path overall. So you've got all these potential solutions with scores. How does it decide which ones to build on? Which ones become the parents for the next generation?
Good question. All the generated solutions and their scores go into this evolutionary database. This isn't just a simple list. It's structured to guide the search. It draws inspiration from algorithms like MAP elites and island models. The key idea is balancing exploration, trying totally new stuff, and exploitation, taking the best solutions so far and refining them. You don't want to get stuck in one corner, but you also want to build on success.
Right, that classic exploration versus exploitation trade-off. And to handle all this computation, it's a big distributed system.
Yep. It's set up as a distributed pipeline. You have a controller managing things, lots of LLM samplers proposing code, and lots of evaluation nodes testing the code. It's all asynchronous and designed for high throughput, getting lots of evaluations done over time.
Okay, I think I've got a good handle on the how. Let's talk about the what. What has AlphaEvolve actually done? The paper mentions faster matrix multiplication first. Why is that such a big deal?
Matrix multiplication, it's everywhere in computing, seriously. Training AI, graphics, simulations, scientific computing, it's fundamental. And finding faster ways to do it has been a major quest in computer science for decades, ever since Strassen found a better way back in '69. It boils down to finding clever ways to combine the numbers, technically finding lower rank tensor decompositions, which means fewer multiplications are needed.
And AlphaEvolve actually made a breakthrough here.
It really did. They started it with just the basic problem description and a standard algorithm. And AlphaEvolve discovered new, more efficient ways to multiply matrices for 14 different sizes, beating the previous best-known methods. The headline result is for 4x4 matrices using complex numbers. AlphaEvolve found an algorithm using 48 multiplications. The previous best, Strassen's algorithm, which held the record for this specific case for 56 years, used 49. That's the first improvement in over half a century.
Wow, 56 years. That's incredible. And it wasn't just a tiny tweak, the paper suggests.
No, not at all. It evolved quite sophisticated changes. Figure 4 in the paper shows it modified things like the optimization technique, how the process was initialized, the loss function used to guide it, various hyperparameters. It was a series of, I think, 15 distinct improvements it found along the way. And interestingly, while many results came from a simple starting point, they also found that giving it some initial ideas from researchers could boost performance even more. It suggests a really nice synergy between human insight and the AI's search power.
Amazing. Okay, so fundamental computer science, check. But it didn't stop there.
Yeah.
It tackled some pretty abstract math problems, too.
Yes, and this is another area where it really shone. They applied it to over 50 open problems in different branches of math combinatorics, geometry, packing problems, inequalities, you name it. And the results were pretty stunning. In about 75% of cases, it rediscovered the best-known constructions, but in around 20%, one-fifth of them, it actually surpassed the best-known results, found provably better solutions.
That's huge. Actually pushing the boundary of mathematical knowledge. Can you give some examples?
Sure. So in combinatorics, it improved the upper bound for a classic problem called Erdo's minimum overlap problem. In geometry, it tackled the kissing number problem. How many spheres can touch a central sphere without overlapping? In 11 dimensions, the previous record was 592. AlphaEvolve found a configuration with 593. It also made advances in things like autocorrelation inequalities, uncertainty principles, and different kinds of packing problems, like how densely you can pack shapes or points. Really diverse stuff.
These are seriously hard problems. How did it approach them? Was it building the mathematical objects directly?
Often, especially for problems where checking a solution is fast, it focused on evolving the search strategy itself. So you give it a time limit, tell it the current best-known solution, and its job is to evolve a search algorithm that can find something even better within that time. This often resulted in quite complex, multi-stage search strategies being discovered automatically. Maybe one part is good at finding rough candidates quickly, and another part is excellent at fine-tuning near the end. Automating the design of these heuristics is a powerful capability. And it's worth mentioning, top mathematicians like Javier Gomez-Serrano and even Terence Tao suggested some problems for them to try, which points to the potential for AI as a genuine collaborator in research.
So pure math, fundamental algorithms.
Yeah.
Real potential for discovery. But it's not just theoretical, right? The paper talks about using it inside Google, too.
Exactly. It's not just lab experiments. They've applied AlphaEvolve to optimize some really practical large-scale systems within Google. One big one was improving job scheduling in Borg, which is Google's massive cluster management system. Think of it as a giant resource allocation puzzle. AlphaEvolve evolved a heuristic, a rule of thumb, for deciding which jobs go to which machines. It found a surprisingly simple but really effective rule that beat the complex system already in production. When they deployed it, they recovered, on average, 0.7% of previously stranded computing resources across the entire fleet. That's a huge win at Google's scale.
Wow. A direct impact on efficiency. And they chose AlphaEvolve over, say, deep reinforcement learning for this. Why?
Yeah, the paper highlights that. A key reason was interpretability. Because AlphaEvolve outputs code, engineers can actually understand why the scheduler is making certain decisions. It's also easier to debug and deploy reliably, which is crucial for a system as critical as Borg.
Makes sense. You need to trust and understand what's managing your data centers. What else did it optimize?
Well, sticking with AI, it helped make Google's own Gemini models more efficient to train. There are these low-level software components called kernels, crucial for performance on specialized hardware like TPUs. Manually tuning these is painstaking. AlphaEvolve was used to optimize the tiling strategies within these kernels. The result? An average 23% speed up for those specific kernels, which translated to a 1% reduction in overall Gemini training time. Plus, it cut down the optimization time from potentially months of human effort to just days. And this improved code is now deployed, making Gemini training faster. So it's kind of cool, Gemini via AlphaEvolve, helping to optimize itself.
That's a fantastic feedback loop. And it even touched the hardware design.
It did. They challenged it to optimize the actual hardware description language, Verilog, for an arithmetic circuit in Google's TPUs. The goal was to reduce its physical size and power consumption. AlphaEvolve found a simple code change, basically removing some redundant bits that achieved this. TPU designers validated it, and it's now part of the hardware design. That's Gemini's first direct contribution, through AlphaEvolve to TPU circuits. Communicating the change directly in Verilog was a big plus, too.
Incredible. Software, hardware. What about the code generated by compilers? That seems like a really tough nut to crack.
It really is. Compilers already do a ton of optimization. But yes, AlphaEvolve was tasked with optimizing the low-level intermediate representation, or IR, generated by the XLA compiler. Specifically, for parts of the flash attention kernel, super important for transformers, and also the pre-post processing code used when running models on GPUs. This IR is normally just for debugging. It's not meant to be easy to optimize further, but AlphaEvolve managed significant speedups. 32% for the flash attention kernel itself, and 15% for the surrounding data processing code. This suggests potential for folding these kinds of AI-discovered optimizations back into the compilers themselves in the future.
Just amazing results across such a diverse range of hard problems. It really underscores the potential here. They also did some tests where they deliberately broke parts of AlphaEvolve, right? The ablation studies. What did they show?
Yes, they did those for the matrix multiplication and kissing number problems. They basically switched off different components, one by one, the evolutionary part, the rich context in the prompts, the meta prompts, evolving whole files using the best LLMs to see what impact each part had. The consistent finding was that pretty much every component contributed significantly to the success. You needed the whole integrated system to get those top results.
So it's really the combination, the synergy of all these pieces, the evolution, the smart LLMs, the context, the automated testing that makes it work so well.
Exactly. It's not just one magic ingredient. It's the whole recipe working together.
Well, this has been a truly eye-opening deep dive. AlphaEvolve.
Yeah.
It seems clear this kind of technology could really change how we discover algorithms, do science, and even optimize the complex systems running our world. If you had to boil it down, what are the absolute key takeaways for our listeners?
I'd say the main things are AlphaEvolve's proven ability to make genuinely novel discoveries, like the matrix multiplication breakthrough, and also deliver practical, real-world optimizations, like in Google systems. It does this by cleverly combining large language models with an evolutionary search process, all grounded by automated evaluation. The breadth of applications from pure math to hardware design is also really striking.
And thinking forward, it really sparks the imagination, doesn't it? We've seen AI get good at solving problems we already know how to define, but this feels different. AI discovering genuinely new ways of doing things, new principles, new solutions. So, a final thought for you, the listener. Based on what we've discussed, where do you see this going? What fields might be totally transformed next by AI that can not just optimize, but truly innovate in code and algorithms?
That's the big question, isn't it? And if you want to dig deeper into the specifics we talked about today, the white paper is available, and they've released supplementary materials too, like interactive notebooks for the math results and the matrix algorithms. Definitely worth checking out if you're interested.
It certainly feels like we're seeing the start of a new chapter in AI-powered discovery and innovation. Thanks so much for walking us through it.
My pleasure. Fascinating stuff.
And don't forget to subscribe to Revise and Resubmit on Spotify and Apple Podcasts. Until next time, keep those minds curious, keep questioning, and keep revising and resubmitting.
রিভাইজ অ্যান্ড রিসাবমিটে স্বাগতম। আমি প্যাভলভ।
আর আমি নিকিতা।
আজকে আমরা একটা বেশ ইন্টারেস্টিং গবেষণাপত্র নিয়ে কথা বলবো,
গুগল ডিপমাইন্ডের একটা নতুন গবেষণা নিয়ে কিন্তু বেশ কথা হচ্ছে, AlphaEvolve, তাই না?
হ্যাঁ হ্যাঁ, AlphaEvolve।
আজকের আলোচনায় আমরা একটু এর ভেতরে ঢুকতে চাই। মানে এটা ঠিক কি, কাজ করে কিভাবে, আর কেন এটা নিয়ে এত হইচই?
একদম। আর এটা কিন্তু শুধু একটা নতুন কোডিং টুল ভাবলে ভুল হবে।
ও
হ্যাঁ, এটা আসলে সমস্যা সমাধানের একটা নতুন অ্যাপ্রোচ। এর মূলে আছে তো ওই বড় ল্যাঙ্গুয়েজ মডেল বা LLM।
হ্যাঁ, LLM তো জানি, কোড লিখতে বা বুঝতে পারে।
ঠিক, AlphaEvolve এই ক্ষমতাকেই কাজে লাগায়, কিন্তু সাথে জুড়ে দিয়েছে একটা বিবর্তনমূলক বা ইভলিউশনারি পদ্ধতি।
বিবর্তনমূলক পদ্ধতি, সেটা কি রকম? তাহলে এটা কি শুধুই একটা কোডিং টুল নয়?
না, ঠিক তা নয়। ধরুন অনেকটা প্রাকৃতিক নির্বাচনের মতো।
আচ্ছা।
AlphaEvolve প্রথমে কোডের অনেকগুলো ভার্সন তৈরি করে, তারপর নিজেই পরীক্ষা করে দেখে কোনগুলো ভালো কাজ করছে। যেগুলো ভালো পারফর্ম করে সেগুলো টিকে থাকে, আর সেগুলোর উপর ভিত্তি করে আরও ভালো ভার্সন বানানোর চেষ্টা করে। এই পুরো ব্যাপারটা চালানোর জন্য জেমিনি 2.0 ফ্ল্যাশ বা প্রো এর মতো খুব পাওয়ারফুল LLM ব্যবহার করে।
ইন্টারেস্টিং তো। তার মানে কোডটা নিজে নিজেই উন্নত হতে থাকে। ব্যবহারকারীকে কি করতে হয়?
ব্যবহারকারীকে মূলত দুটো জিনিস দিতে হয়। এক, সমস্যাটা ঠিক কি, আর দুই, সমাধানটা কতটা ভালো সেটা মাপার উপায়টা কি, ওই যে ইভ্যালুয়েশন প্রসেস।
আচ্ছা আচ্ছা, বাকিটা AlphaEvolve নিজে করে?
হ্যাঁ, বাকিটা ওই সামলায়। LLM ব্যবহার করে আগের সলিউশন থেকে শেখে নতুন কোড বানায়।
নতুন কোড মানে পুরোটা লেখে?
না না, সাধারণত পুরোটা না। কোডের কোন অংশটা বদলাতে হবে শুধু সেটুকুই সাজেস্ট করে। এটাকে বলে ডিফ ফরম্যাট।
ও আচ্ছা।
তারপর নিজে নিজেই টেস্ট করে দেখে কোনটা বেটার।
আগের সিস্টেম যেমন ফান সার্চ শুনেছিলাম, সেটার থেকে এটা আলাদা কোথায়?
ভালো পয়েন্ট। ফান সার্চ মূলত একটা ফাংশনের ভেতরে কাজ করতো, আর শুধু পাইথনে।
হ্যাঁ হ্যাঁ। তাহলে এর আসল পাওয়ারটা কোথায় দেখা গেছে? এমন কিছু কি করেছে যা আগে কেউ পারেনি?
এখানেই তো আসল ব্যাপারটা। যেমন ধরুন ম্যাট্রিক্স গুণন।
ম্যাট্রিক্স মাল্টিপ্লিকেশন, আচ্ছা।
4x4 জটিল ম্যাট্রিক্সের জন্য প্রায় 56 বছর ধরে স্ট্র্যাজেনের একটা পদ্ধতি ছিল। 49টা স্কেলার গুণন লাগতো, ওটাই বেস্ট ধরা হতো।
জানি।
AlphaEvolve কিন্তু 48টা গুণনে ওটা করার একটা নতুন অ্যালগোরিদম খুঁজে বের করেছে, আর সেটা প্রমাণিতভাবে সঠিক।
বলেন কি? মাত্র একটা গুণ কমিয়েছে? কিন্তু এটা তো বিশাল ব্যাপার।
অবশ্যই, কারণ বহু বছর ধরে এটা সম্ভব হয়নি। শুধু এটাই মা, 14টা বিভিন্ন সাইজের ম্যাট্রিক্স গুণনের ক্ষেত্রেও কিন্তু ও সেরা অ্যালগোরিদমকে আরও উন্নত করেছে।
অবিশ্বাস্য। বছরের পর বছরের সেরা চেষ্টাকেও ছাড়িয়ে গেল। আচ্ছা, এটা কি শুধু অ্যালগোরিদমেই? গণিতেও কি কিছু করেছে?
হ্যাঁ, গণিতেও এর ভালো প্রভাব আছে। 50টারও বেশি আনসলভড ম্যাথ প্রবলেমে এটা ব্যবহার করা হয়েছে।
তাই নাকি?
75% ক্ষেত্রে দেখা গেছে মানুষ আগে যেসব ভালো স্ট্রাকচার খুঁজে পেয়েছিল সেগুলো এটা আবার খুঁজে পেয়েছে। আর প্রায় 20% ক্ষেত্রে আগের রেকর্ড ভেঙে নতুন আরও ভালো সমাধান দিয়েছে। যেমন ধরুন এডসের মিনিমাম ওভারল্যাপ প্রবলেম, বা 11 ডাইমেনশনে কিসিং নাম্বার প্রবলেমের লোয়ার বাউন্ড, এগুলো ইমপ্রুভ করেছে।
ইন্টারেস্টিং।
আর কিছু ক্ষেত্রে ও সরাসরি সমাধানটা খুঁজে দেয়নি, বরং সমাধানটা খোঁজার জন্য আরও ভালো হিউরিস্টিক সার্চ অ্যালগোরিদম তৈরি করেছে। বলতে পারেন সমস্যা সমাধানের একটা ভালো শর্টকাট বা নিয়ম বানিয়ে দিয়েছে।
আচ্ছা আচ্ছা, বুঝতে পারছি। তার শুধু থিওরি নয়, বাস্তবেও এর প্রয়োগ হচ্ছে গুগলের মতো জায়গায়।
হ্যাঁ, হচ্ছে তো, এবং বেশ কিছু গুরুত্বপূর্ণ জায়গায়। যেমন ধরুন গুগলের যে বিশাল ডেটা সেন্টার, সেখানে কম্পিউটিংয়ের কাজগুলো ভাগ করে দেওয়ার যে নিয়ম, জব শিডিউলিং, সেটাকে ইমপ্রুভ করেছে। তাতে প্রায় 0.7% কম্পিউট রিসোর্স সাশ্রয় হয়েছে। শুনতে কম মনে হলেও গুগলের স্কেলে এটা বিশাল।
হ্যাঁ, তা তো বটেই। আর
জেমিনি মডেল ট্রেন করার জন্য কিছু বিশেষ কোড লাগে, কার্নেল বলে। AlphaEvolve সেগুলো অপটিমাইজ করে গড়ে 25% ফাস্ট করেছে।
30%? দারুণ।
এর ফলে পুরো জেমিনি ট্রেনিংয়ের সময় প্রায় 1% কমে গেছে। মজার ব্যাপার হলো AlphaEvolve তো জেমিনি মডেল ব্যবহার করেই চলে, তাই না?
হ্যাঁ।
তার ও এখানে নিজেকেই আরও ফাস্ট হতে সাহায্য করেছে।
বাবা, এটা তো দারুণ একটা লুপ। আর কিছু?
আরও আছে। গুগলের নিজেদের চিপ TPU, সেটার হার্ডওয়্যার ডিজাইনেও সাহায্য করেছে। ভ্যারিলগ কোডে অপ্রয়োজনীয় অংশ বাদ দিয়ে সার্কিট সিম্পলিফাই করেছে।
হার্ডওয়্যার লেভেলেও?
হ্যাঁ, এমনকি কম্পাইলার যে কোড জেনারেট করে, যেমন ধরুন ফ্ল্যাশ অ্যাটেনশনের জন্য XLAIR, সেটাকেও সরাসরি অপটিমাইজ করে 32 পর্যন্ত স্পিড আপ করেছে।
ওয়াও, তার মানে এর অ্যাপ্লিকেশন তো অনেক বিস্তৃত।
ঠিক।
এত কিছু যখন পারছে, এর সীমাবদ্ধতা কি? এমন কিছু আছে যা এটা পারে না?
একটা প্রধান সীমাবদ্ধতা আছে। সমস্যাটা সমাধান যে ভালো হলো না খারাপ হলো সেটা মেশিনকে অটোমেটিক্যালি বুঝতে পারতে হবে, মানে মূল্যায়নটা অটোমেটেড হতে হবে।
ও আচ্ছা।
যেখানে ধরুন মানুষের অবজারভেশন লাগে বা ম্যানুয়ালি টেস্ট করতে হয়, সেখানে AlphaEvolve সরাসরি কাজ করতে পারে না, কারণ ও তো নিজেই টেস্ট করে ভালো মন্দ বোঝে।
বুঝতে পারছি। অটোমেটেড ফিডব্যাক লুপটা খুব জরুরি।
একদম।
তাহলে যদি একটু গুছিয়ে বলি, AlphaEvolve হলো বড় ল্যাঙ্গুয়েজ মডেল আর এই বিবর্তনমূলক পদ্ধতির একটা পাওয়ারফুল কম্বিনেশন,
ঠিক,
যেটা কোড জেনারেট করে এবং নিজে নিজেই সেটাকে উন্নত করে বিজ্ঞান, গণিত, ইঞ্জিনিয়ারিংয়ের কঠিন সব সমস্যা সমাধান করছে। কিন্তু শর্ত হলো সেই সমাধানের মান অটোমেটিক্যালি মাপা যেতে হবে।
একেবারে নিখুঁত সারসংক্ষেপ।
চমৎকার আলোচনা হলো।
হ্যাঁ, আর শেষে একটা প্রশ্ন রেখে যাই ভাবার জন্য।
বলুন।
যদি আর্টিফিশিয়াল ইন্টেলিজেন্স বা এআই এভাবে অ্যালগরিদম আবিষ্কার করতে পারে যা কিনা কয়েক দশক ধরে মানুষের সেরা চেষ্টাকেও ছাড়িয়ে যাচ্ছে, এমনকি নিজেকেই নিজে উন্নত করছে, তাহলে ভবিষ্যতে বিজ্ঞান বা প্রযুক্তির অগ্রগতি ঠিক কতটা দ্রুত হতে পারে? আমরা কি গবেষণা করার পদ্ধতিতেই একটা বিরাট পরিবর্তনের মুখে দাঁড়িয়ে? এই প্রশ্নটা কিন্তু ভাবায়।